This is homework 2 part A of separations. So what we have today is we're going to be deriving the Rackford-Rice equation from a vapor-liquid equilibrium, and we're going to show that even that it is a monotonic function of the vapor mole fraction. So we're going to start with defining our total composition, which is just vapor plus liquid, and this is in terms of I equals 1, 2, 3, all the way to n. We want to expand this using ZIF, and this will give us YIV plus XIL. This is like the vapor composition fractions, and I want to go ahead and isolate our ZI by moving our F over, so we get ZI equals YI V over F plus XI L over F. And if we take a look at the VF, this is our vapor fraction, which is also equal to phi. So ZI equals YI phi plus XI times 1 minus phi. This is just because this is more of the remainder of phi, since this is kind of like saying it's like the remainder. We need everything to be 100%, so if this is one value, this needs to make up for the rest. I want to also keep in mind of our k constant, which is yi over xi, or Raoult's law, and how this is going to relate is we're going to make this yi equals ki times xi, and we can go ahead and substitute that in, so then we're left with ki xi phi plus xi times 1 minus phi. As you can see, we could also go ahead and take out our xi variable, so we're left with ki phi plus 1 minus phi. And then we're going to solve for xi, so then we have our zi over 1 plus ki phi minus phi. Now let's take the sum of both sides. This will come out to 1, where we know what zi and ki we can find. The only unknown variable really is our phi. Now, since we did take this in terms of where is it? Yi equals kix, let's try and do it the opposite way, where xi equals yi over ki. So we're just going to do basically the same thing, where we take our zi equals our yi phi plus our yi over ki times 1 minus phi. And then we're going to just go ahead and basically just put this ki to the left side and multiply that over for both sides. So we're left with ki yi times pi, or phi, plus yi times 1 minus phi. You can see we can now go ahead and separate our yi from the rest of this equation. So we're left with 1 minus phi. And then since we are looking for yi, we're going to go ahead and make yi equals ki zi over 1 plus ki phi minus phi. I think that's correct. Yep. So we're going to do the same thing and take the summation, and this is also equal to 1. But now let's say that yi minus summation of xi. This is basically just saying 1 minus 1 equals 0. This is great because we can go ahead and expand this. Ki zi over 1 plus ki phi minus that minus r summation of zi over, which is minus phi, which equals 0. And then if we just expand this out, or just simplify this out, we're left with zi, which equals 1 plus ki over, or I guess it'd be minus which equals 0. And significance of this equation is that this is the equation we're going to use in Colab, and this just basically states our monotonic function, which basically means it's constantly increasing or decreasing. And this is how we're going to determine a accurate guess for our vapor mole fraction, and we're also going to use this to help determine whether that sort of guess is accurate or not. Okay, so this is the Colab section to determining our implementing our Rackford-Rice calculation. So we're going to check that the flash occurs in the two phase regions, explain how the bubble pressure and dew pressures can be found or can be used to infer an initial guess for the vapor mole fraction, and apply our function to the flash calculation of a feed comprising of 40 by 60 moles of benzene and toluene at a pressure 1 bar and temperature 370 Kelvin. So we're going to define our flash point first. So we're going to use our Z value and our pressure and temperature, and then we're going to define our dew pressure, which and we're going to use our Z value and temperature. And then for bubble pressure, we're going to do pretty much the same, except we're defining it bubble, but it's also Z and temperature. And then we're going to throw in an if statement showing whether pressure, or what happens if pressure is greater than dew pressure. And in this case, if pressure is greater than dew pressure, then we're going to be left with all liquid. So we're going to return with the syntax of all liquid. And if pressure is greater than bubble pressure, then we're left with all vapor. Now we will go ahead and define our vapor fraction guess, which Gemini got a little wrong. It's our bubble pressure minus our pressure divided by bubble pressure minus our dew pressure. Then we want to go ahead and define our K value, which is our vapor pressure at a certain temperature divided by our regular pressure. And then we want to also define our roots that we're going to be using. So we're going to go ahead and define fruit and phi. Now we'll be returning with our equation that we used earlier, or that we found earlier, our Radcliffe-Rice equation. And we're going to be using our JAX function to help us solve that. So we'll do jnp.sum and then write down our Radcliffe-Rice, which is divided by 1 plus phi times k minus phi. We can double check that right here. Yep. Actually, k minus 1. Yep, that looks right. And then we're going to define our fruit prime using jax.grad, and this is just going to help us solve those derivatives to help find the composition, or the change in vapor fraction over composition, I believe. And then we'll also define our fruit, which is jax.jit respect to fruit. Okay, so now what we're going to do is we're going to go ahead and try to find our vapor fractions, which is phi, and we're going to have sp.optimize, kind of right, root underscore scalar, still not right, just fruit, where our x prime, or x x naught is our guess. Our method will be Newton, and our f prime is equal to, yep, that's it, fruit underscore prime dot root. We're going to have our x defined as z divided by 1 plus phi times k minus phi, which is kind of similar to our previous equation, but slightly different. And then we have y equals k times x. And then we want to return with phi and x and y. Let's see if that works. It might take a minute since it's running quite a bit of code. Okay, yep, it works. Alright, now we can get on to our flash calculation, which will give us our guesses. So we have our flash function, and then our ratio, which was given in the problem statement, of a feed comprising of 40 by 60 moles of benzene slash toluene. So that's right there. And then we will have our pressure, which is in pascals. So it's 1 times 10 to the 5th. And then our temperature. And that should be it. That's our flash calculation. And we'll, oh, this might have to just be lowercase. One sec. Okay, found the problem. The bubble pressure and dew pressure were switched, so I've switched them now, but the dew pressure was up here, which would make sense because then if it's dew pressure, it can't be all liquid. So it's bubble pressure where we get all liquid, and then the signage was uh, opposing the other way. So yep, so here we have our vapor fraction, and then we have our liquid composition of 33.5% for benzene, and then 66.5% for toluene, and then our vapor composition of 55.3% benzene and 44.7% toluene.